Hello and welcome to Animated Education. Today we are going to continue talking about units of measure, and I'll solve some pretty advanced problems connected to that topic. So our first problem is, suppose that while lying on a beach near the equator, watching the sun set over a calm ocean, you start a stopwatch just as the top of the sun disappears. You then stand, elevating your eyes by a height equal to 1.7 meters, and stop the watch, then the top of the sun again disappears. If the elapsed time is 11.1 seconds, what is the radius r of Earth? So you're asked to find a radius of Earth. However, I don't like what time they give us, because I'll say why it is later. So let's say that our time is 10.044 seconds. Let's say our time is this. And height is 1.7 meters. That's an average height of a human. So what basically this problem says is that we have a sun here. This is sun, and this is Earth. This is the center of Earth. And the rays of a sun is going like that. So we are laying down at beach at point this. Let me take an okay. At this point, and we stop seeing the sun. We stand up, and we start seeing sun again. Once our Earth rotates, and we stop seeing it again. Now let's make a picture, a better mathematical picture of that. So we have a ray here. This is a sun's ray, and this is a center of our Earth. This is our radius, and because the Earth is a bit round, here is also radius. However, we say that this roundness is small enough to ignore, and we say let's draw a line here, okay, and ignore this. This is some angle alpha, and this is our height. Maybe I'll do it in a different color. This is our height, h. This is a right angle. So what we need to do, firstly, we need to calculate this angle. We want to know how much the Earth rotated. So alpha divided by 360 degrees is the same thing as our fraction of time divided by whole 24 hours, or the whole day, because as you can see, this is a proportion. It takes a small amount of time, very small amount in time, in fact, to rotate a bit this angle alpha. Also, it takes 24 hours to rotate fully. What we get from that? We get that our alpha is, we're multiplying t and 360, so, and divided by 24. However, we want to know our time is given in seconds, so we want to change this 24 hours in seconds, so we multiply it by 3,600, because that is how many seconds are in 1 hour. You get this from multiplying 60 minutes and 60 seconds. So once we do that, we put, instead of t, 10.044, multiply it by 360 degrees, divide it by all this thing, and we get that our alpha is equal to 0.04185 degrees. So it's extremely small. Now let's go back to our picture and we see that this is the right angle, and we have two sides of this triangle because here is a triangle. Let's say this is A, this point is B, and this is C. This is a triangle. So from this we get that we can use cosine theorem. So we can write that cosine alpha is equal to, this is the right triangle, so we take this leg and divide it by hypotenuse, r plus a hash. So this is r divided by r plus h. So from this we can express our r and get our final answer. So we're multiplying both sides by r plus h because this is definitely non-zero. If it would be mathematics, you couldn't do that because you don't know if these two aren't zero. But well, we know for sure that this is more than zero and this is more than zero, and we are adding them. So this will give us like that. Now let's multiply r by cosine alpha and h by cosine alpha. So let's move this r to the other, no, better, let's move this to this side here. So we get excuse me, this is minus here, I made a mistake, this is minus, and now we can write that h cosine alpha is equal to r 1 minus cosine alpha. I took r before parentheses, and you can see I didn't change anything in fact, because you can multiply r by 1 and cosine alpha and you will get the same. Now let's divide this both sides by 1 minus cosine alpha. You probably don't see this, but I'm dividing by this. So we get that our r is h cosine alpha divided by 1 minus cosine alpha. Now we know that our alpha is 0.04185 degrees, so we get that our radius is 1.7 meters times cosine of 0.04185 degrees divided by 1 minus cosine of the same amount of degrees, and this will give us that the radius of the Earth is 6,372,842 meters. And that is, in fact, very close to an actual radius of an Earth. However, now let's go back to our original problem, and they gave us time that was 11.1 second. If you worked through a problem with this number, your answer would be way off. Instead of 6 million, you would have somewhere around 5 million meters. So, however, as you can see, I changed time not very much. I changed it to be 10.044 seconds. So this is not a big difference. However, if we are calculating the Earth radius in such a way, it is a very big difference. So, well, it's not the best way to calculate the radius of an Earth. However, it's theoretically possible. Let's consider the following. Water is poured into a container that has a small leak. The mass m of the water is given as a function of time by m. M is equal to 5t to the power of 0.8 minus 3t plus 20. And we know that time is more than 0, more or equal to 0. Mass is in grams, and t is in seconds. At what time is the water mass greatest? Okay, so let's deal with that at first. So this is not extremely hard exercise if we are looking at it from physics side. However, it requires to know how to find the maximum value of a function. So I consider it relatively a hard exercise, simply because of the need of mathematics here. So the first thing to do to find a maximum value of this function is to find a derivative of this. So a derivative of this function would be 5 times 0.8 times t to the power of minus 0.2 minus 3, and this will give us 0, so I won't write it. Now, once we do that, we need to solve this equation when we say that this is equal to 0. So we get that 4t to the power of minus 0.2 minus 3 is equal to 0. Now, let's rewrite it like that, so it would be easier to understand what this is, because this is 1 over 5, and if something is, let's say a is in a power of 1 over n, it is the same thing as an nth root of an a. So minus 3 is equal to 0. Now let's move this 3 to the other side, and so plus 3, and also let's multiply it by a fifth root of t. Okay, so once we do that, we get this is 4 equal to 3 times a fifth root of t. Now let's divide both sides by 3, and we get that a square root of a fifth root of t is equal to 4 divided by 3. Now we need to raise both sides of this equation by a power of 5. So we raise this by a power of 5 and this by a power of 5, and we get that t is equal to 1024 over 243, and this is approximately 4.21 seconds. Because we are asked to find the maximum value of this function, and this is a physics problem, I'm almost 100% sure that this is a maximum value. However, for the sake of mathematics, we should check it. So let's draw a line of numbers. This is t, and we put our 4.21 seconds here. We draw two intervals, and this is this is a derivative, a function of derivative, and this is an actual function. Okay, so now we need to check this. So if our function of our derivative is greater than 0 or less than 0 in these two intervals. So let's say 1 is somewhere here, so we can just put 1 in our function. So once we put 1 in this function, we would get that this is, well, 4 minus 3, 1, so it's greater than 0. Now, if you put, let's say, 5 in this function, so we would get that this is equal to, so we would get that this is less than 0. I'll skip the calculation and leave it for you, because all I need to do is put 5 here, okay, instead of this t. So you would get that this is less than 0. Now the function here is increasing, and in this interval it's decreasing. So it reached its maximum value at this point. So t max is definitely 4.21 seconds. This is our answer. Okay, so the second part of the problem asked us when the mass of water in the container is the greatest. So here are asked to calculate m max. So we have our function. A function looked like this. I'll just rewrite it from our original problem. So this was m of t. So, and we got that t max was that this function is reaches its peak at this value when t is approximately 4.21 seconds. However, I don't want to approximate this because it will give me the more accurate answer. So what we need to do here is to calculate m when in this time moment. And once we do that, that's also a job of your calculator, and I don't think it's necessary. Basically, all you need to do is to put this number 1024 divided by 243 instead of every t in this equation. And once you do that, you get that the mass is equal to 24.16 grams, and this is your answer. Okay, so let's look again at our problem. The last part of the problem asks us to find a rate of change in kilograms per minute of this function, so of the mass of the water. Okay, so we have our function m is equal to 5 t to the power of 0.8 minus 3t plus 20. Now this is grams per second, but we want kilograms per minute. So what we need to do to get kilograms per minute is to multiply this equation by 60 and divide it by 1000. Once you divide it by 1000, you'll get kilograms per second, and once you multiply it by 60, you get kilograms per minute. So our equation now looks like this: 0.3 t to the power of 0.8 minus 0.18 t plus 1.2. This is now kilograms per minute. Now, in order to find the rate of change, we need to take a derivative of this, and the derivative would be 0.24 divided by a fifth root of t minus 0.18. So this is, this is a derivative. So this is basically a rate of change. Now, we are asked to find a rate of change in this given moment when t is equal to 2 seconds. So instead of this t, we need to put 2. So our derivative is equal to 0.24 over a fifth root of 2 minus 0.18. And this would approximately be 0.029, and this is the rate of change. So I will not do the last problem because all this is just putting different t value in our equation. But this is basically how you get the rate of change. Okay, so yeah, that's about it for this video. I hope you understood. I know this wasn't some very easy exercises. They were pretty advanced, but I hope you understood, and see you next time.